In this video I'll be looking at particle physics, which is part of Unit 4 of EDEXCEL physics, EDEXCEL A2 physics, and we're looking at task 4 of the ISP. So in task 4 we'll be talking about a bit more about the structure of matter and particle accelerators, which we've covered in the past, and looking towards maybe some of the longer answer questions based around that. Okay, so the questions will be based around these areas. So let's go straight to task 4. We've got some questions over here. So not necessarily questions with long answers, but also the variety of questions that you'll be getting in an exam. So some of them were multiple choice, as over here, and some of them were quite short, which is like a question 11 or something like that. But also one of the questions towards the back end of the paper, the 12 markers that sort of build and tie together many areas. Okay, so let's look at question 13. So talking about an experimental LHC, talk about the idea of a tera electron volt, and they talk about the fact that it has 5,000 superconducting magnets. So you can assume it's going to have something to do with E equals mc squared in there. You can assume it's going to have something to do with magnetic fields in there. You can assume it might have a circular motion equation question in there by the fact they're giving us the radius, the circumference of this accelerator. So they're saying that they're trying to create a Higgs particle, and they've given an upper limit for the rest mass of the Higgs being 251 gigaelectron volts over c squared. So remember, if that's the rest mass of it, the amount of energy actually required to make it is going to be 251 gigaelectron volts. Remember, energy converts to mass and mass converts back. So 7 teravolts is much greater than 251 gigaelectron volts, and therefore the LHC should be able to create the particle, because energy, the proton that's got this 7 teravolts is greater than the energy required to make Higgs. So the energy of that proton is converted to mass, and there's more than enough energy to make one Higgs. Right. So, provided the energy of an accelerated particle is much greater than its rest mass energy, its momentum can be calculated by that equation over there. Okay, so that's momentum is equal to energy over c. So show, c being the speed of light, show that a 7 tera electron volt proton has much greater, has an energy much greater than its rest mass. Okay, so first you figure out the rest mass energy of a proton, and then you figure out what 7 tera electron volts is in terms of energy as well. Or what you could do in terms of joules as well. Or what you could do is figure out the rest mass energy of a proton and get that into electron volts. So how do we figure out the rest mass energy? Well, that's pretty straightforward. That's E equals mc squared, where m is the mass of a proton, 1.67 times 10 to the minus 1.67 times 10 to the minus 27. You times that by c squared and you end up with about 1.5 times 10 to the minus 10. So that's how many joules it is. You want that in electron volts, so you can do a direct comparison. So you divide it by 1.6 times 10 to the minus 19, and you end up with 9.4ish times 10 to the 8. Okay, so 9.4 times 10 to the 8. So that's not even a gigaelectron volt yet, because gigas times 10 to the 9. So about a gigaelectron volt. No, not even about a gigaelectron volt. About a tenth of a gigaelectron volt. No, sorry, I was right the first time. About a gigaelectron volt. Okay, so you're looking at about a gigaelectron volt. So nowhere near a teraelectron volt yet. Out by 1,000. Okay, so it's got much less energy, and we've proved that by doing that calculation. Right, show that the momentum of a 7 tera electron volt proton is about 5 times 10 to the minus 17 kilogram meters per second. So the first thing we're going to do is worry about this unit here. We want to get this unit here out of tera electron volts and into joules, which will therefore allow us to figure out the momentum. Okay, because this particle energy over here must be in joules and not in electron volts. So, first thing you need to do is, you do energy over c. You figure out what the energy is by timesing the 7 times 10 to the minus, times 10 to the 12, sorry, so 7 times 10 to the 12, and you multiply that by the value of an electron volt, so that's 1.6 times 10 to the minus 19. So we're using the equation that we're given here. Okay, so I'm just switch my pen. So we do 7 times 10 to the 12 times by 1.6 times 10 to the minus 19, the value of 1 electron volt, and then we need to divide that by c squared, which is 3 times 10 to the 8 squared. Once you do that, that will tell us the momentum. Very straightforward. and you end up with about 4-ish times 10 to the minus 15. There you go, 3.7 times 10 to the minus 15. Nice question to get. Right, calculate the magnetic flux. Says, as we predicted, magnetic flux will be asked near. Calculate the magnetic flux density provided by the superconducting magnets. Ooh, right, okay. Cyclotron, cyclical accelerator. We've got momentum. They've just figured out momentum. We've been given circumference and not radius, but we can figure out radius, so we've got to think of an equation. So by looking at the equation list, we've got this equation here. Well, we know the top bit is just momentum. So we've got the momentum of our relativistic particle, which is slightly different. And we've got everything else we need. We can figure out from our circumference. And these values, well, those two values we've got and that we want. So we rearrange for B. So B is equal to momentum, not density, sorry, momentum time divided by R times by Q. The momentum is our value from before. R, well, we're going to figure that out from the circumference. So remember, circumference is equal to 2 pi r. Okay, so the radius is equal to circumference divided by 2 pi. Okay, so that therefore gives us, sorry, my camera is just having a small fit there. There we go. Okay, so circumference is equal to 2 pi r. So radius is therefore equal to circumference divided by 2 pi. That then, so now we've got the idea of the radius of this. We've got the charge. Okay, it's 1.6 times 10 to the minus 19. It's just a proton. We've got the momentum from the previous question, and we can figure out the strength of our magnetic field then. It's a nice 4-mark question if I remember correctly. Yeah, 4-mark question. Very good. So a student says the magnetic field needs to be in a vertical direction to cause the protons to move, to travel in a horizontal circle. Okay, so you can see what he's trying to get at is the idea that things must be perpendicular to each other. So yes, he's right, okay, because motion and force need to be acting in the horizontal plane essentially. Okay, both the motion and the force need to be acting in the same plane. So motion, force, and the magnetic field all need to be perpendicular to each other, and we know that from the motor rule essentially. Okay, so the motor rule, we drive on the left hand side, motors are on the left hand side of the road. Okay, so it's the left hand rule, so it's Fleming's left hand rule is essentially what we're using. Okay, so they're saying that the magnetic field, first finger field, and the second finger current, as direction, the movement of the charged particle, must be perpendicular alongside the force that's being applied. So these three must all be perpendicular to each other. Okay, that's exactly how this idea works. Right. 14. Okay, a top quark has a mass of 171 giga-electron volts over c squared. So its mass in kilograms is about, okay, so that's rest mass energy of 171 giga-electron volts. Okay, so we just need to use E equals mc squared, rearrange for m to allow us, sorry no, then we just multiply by, 171 giga-electron volts over c squared. Hold on, let me just work this with my calculator to check that I've got my thought process right on this. These are easy questions to make mistakes on. Times 10 to the 9. 10 to the 9. 5, 1, 3, 10, 8. Divided by 3. Just 8 again. 9, 10. And then times it by 1.6. 3.0 must be 5. Yeah, okay. So it is exactly as I thought. So what we need to do is we need to sort of multiply out this factor here. Okay, we need to get it out of electron volts and out of this idea c squared. So essentially you multiply it through by this factor. You multiply 171 by whatever the value of this number here is. Remember, all we've done is we've sort of made a bracket and taken this out of here. So remember, when you factorize and you take out the common factor and put it in front of the bracket, that's all you're doing here. So you've just taken this out. So you need to multiply it back in. So you need to multiply in the giga-electron volt over c squared. So you multiply by giga electron volts, that's 1.6 times 10 to the minus 19 times 10 to the 6, because it's not times 10 to the 9, sorry, because it's giga. And then you divide by 3 times 10 to the 8 squared. Okay, so that gets that all into kilograms essentially. Okay, because remember that is a unit of mass. Let me lay that out to you clearly on this little patch of paper over it. Okay, so giga. Okay, I'm going for the blue pen which isn't working. I should really throw that in the bin. Giga electron volts over c squared is just a unit of mass. So that is essentially telling you how much mass you have. Okay. Remember, this is the factor that I'm talking about that has been taken out of this number to make it an easy number to compare. So we need to multiply it all back in. Okay, so you do that times by the giga times by the electron volt divided by the 3 times 10 to the 8 squared, and that value there ends up giving you 3 times 10 to the minus 25, which is C. Okay, 15, it's a positive pion. Okay, so it's going to be positive. Remember, up quarks are positive, down quarks are negative. So positive pion is composed of which combination of quarks? Okay, so it's got to have a quark anti-quark pair, because we know a pion is a meson, so it automatically eliminates A and D. It's got to end up being positive. Okay, so downs are negative as are anti-ups, so therefore it must be C. Pretty straightforward process of elimination for that one. Play that back if you need to follow that through step by step in terms of how I figured that out so quickly. Last question in terms of ISP task 4. To state what is meant by a baryon. So baryons are made up of 3 quarks, remember. In beta minus decay, a neutron becomes a proton. Explain what happens in the quark structure of the baryon changes in this process. Okay, so if it's going from a neutron into a proton, it ends up going from down, down, up to down, up, up. So one down becomes an up, essentially. But the way you really need to show it is that a neutron, I might as well write it out. Okay, so a neutron is down, down, up, and that becomes a proton, which is down, up, up. So one down quark has become an up quark in beta minus decay. That is the end of ISP task 4. Okay, so we've got one more task left on this, which again some summary questions. This time based more around the ideas of particle accelerators. Okay, thank you very much for watching, guys.